Hello, everybody. We're going to go ahead and get started in just about a minute or so. If you could do me one favor, if I can get a few people to click on the raise hand button, there should be a raise hand buttons there. This is just so I know that the sound is going through. So, okay, I already got a bunch of people raising their hands, so I appreciate it. So we'll go ahead and start in just about a minute here. All right. Welcome, everybody. Welcome to the November Statist technical webinar. My name is Martin Bessener, and I'm the president and CTO here at Statist. Today we have kind of an interesting topic, a new topic. We're going to be talking about space filling designs and Gaussian process models. So this is something that's pretty new. It's contained in our new product, and I think it's going to be it's going to be very useful to most people. So just kind of some preliminaries. I think everybody's muted right now just for the sake of expediency. So if you have any questions, you can chat them in the messaging feature. What's probably most easiest is if afterwards, if after the presentation, you just send me an email here, just for the sake of time. Sometimes these webinars, we try to keep them at about 40 minutes. And if there are tons of questions, then this kind of gets, we could easily go an hour, 10 minutes or so. So probably the easiest thing is to send me an email afterwards. So, and unfortunately, because we do only have 40 minutes, 45 minutes, this is going to be a very high level overview. We're not going to be, it's going to be mostly practical. It's going to be mostly an introduction to these topics, since this is something that Statist has never really done before. So this is kind of just an intro. What is it, when to use it, how to use it. So we're not going to be getting too deep into the technical details here, which I guess could be a good thing. Okay, so here here's kind of the sketch and outline of what we're going to be doing today. So I'm going to talk just a few slides on our new product called Statist 360. This was launched in October of this year, so just about a month ago. It's essentially an extension, an advanced version of our flagship software, Design Expert. Since space filling designs and Gaussian process models are much more advanced, and they're somewhat not as widely used as something like a factorial design, we've kept it in our more technical product here. I'll then spend the bulk of the webinar talking about space filling designs. What are they? What are the different types of designs? When would you use one? And so on. Afterwards, I'll spend just a little bit on Gaussian process models, which is one way that we can fit data that was collected in a space filling design. And finally, I'll have two simple demos that I want to show. One is just a one-factor tutorial. Another one is a more involved experiment. And then we'll kind of conclude from there. So as you see, there's quite a bit of stuff to talk about in just 40 minutes. So why don't we go ahead and get right into it. So just a few words on Statist 360. So Design Expert, most of you hopefully know Design Expert. It's been one of the leading software packages in DOE, or the design and analysis of experiments. And this was developed in the mid-1980s by Pat Whitcomb. He's the founder of Statist, though he's been retired since last April. He's still around and will do some webinars and consulting here and there, but he's by and large spending most of his time on the beach now. And he was a chemical engineer. So Design Expert was kind of designed, so to speak, with engineering in mind. It wasn't really a statistical package. It was more of an engineering toolkit for R&D people. And Design Expert, or DX, provides cutting edge, easy to use, this is really the key here, easy to use tools that don't require lengthy formal statistical training. So as you can see, this is, I believe, Design Expert 10, and this is the graph of our latest version, Design Expert 13. So you can see that things have progressed quite a bit over the years. Now, the problem is that over the years, we've received, lots of requests, lots of people asking us for more advanced tools. We've always kind of historically focused on, quote unquote, old school DOE, meaning, okay, you get your design layout, you go into the lab, you do your experiment, and you do and analyze the data. However, as I've said, we've received demand for tools that are adjacent to kind of traditional DOE. So things like design and analysis of computer experiments, which is part of what I'm going to be talking about today. Gauge R&R, more computing capabilities, statistical process control, multivariate analysis, and a bunch of other stuff. Unfortunately, we've always had the philosophy of keeping Design Expert as simple as possible and accessible as possible. So, historically, we've usually, tabled these requests and told people that it's not really our wheelhouse. But, the demand just simply was getting bigger and bigger, so we had to do something about it. So, we released Statist 360 just about a month ago, October 4th, 2021. So pretty new stuff. It actually contains a full copy of the Design Expert software. So it's not like it's a second product that you have to buy. However, the first release of Statist 360 also has some of the most highly requested stuff that we've gotten over the past couple years. Space filling designs, Gaussian process models for zero error data. And a lot of times these two bullets here are kind of grouped into something called DOE for computer experiments, although space filling designs and Gaussian process models are not necessarily limited to computer experiments, though they're often associated with them. We also have a scripting tool now that allows you to write scripts, custom scripts, using the Python language. So if you already know any programming or any software and want to write, very complicated analysis tool chains, or you want to bring in something from some, advanced Python package and interface it with Design Expert, or you want to pull data out of Design Expert and you want to, send it over to some other software and then send it back to Design Expert, you can do it using our Python scripting capability. And then there's also some advanced stuff for logistic regression. So that's really all there is about Statist 360. Going forward, Design Expert will continue to be targeted towards engineers, formulators, and others working in R&D. It's not going anywhere. And remember, Statist 360 contains all of DX, so it's you don't need to buy both if you want scripting and you want what's in Design Expert. So going forward, kind of the easy to use bread and butter techniques will go into both Design Expert and Statist 360. However, some of the more advanced stuff, the non-DOE stuff, the highly technical and computational features will only go into Statist 360. So things like measurement system analysis, that's not really traditional, DOE. It's related to DOE. Things like multivariate analysis, more scripting, computing, simulation tools, all that will probably be going into Statist 360 for the sake of keeping Design Expert as simple and straightforward as possible. So that's all I have to say. So the reason why I mention that is because space filling designs and Gaussian process models and everything I'm going to be showing today will be done within Statist 360. So let's get right into it then. Space filling designs. So what are space filling designs? Well, fortunately, the name pretty much gives it away. Space filling designs, it's a type of experimental design that tries to cover, or it tries to spread out your experimental runs in kind of a nice way in the design space. Okay, so what does nice mean here? Well, generally what you don't want is large gaps in the design space. You want the space to be filled. You also don't want, regions where you have tons of points and then other regions where you have, almost no points. So we don't want too many points clustered in the same region. Now, Space filling designs are commonly associated with computer experiments. However, they also have uses in physical or, I call them traditional experiments, meaning, you go out in the lab, you experiment, and you come back. And kind of what the one, neat yet frustrating thing is that space filling designs are still a very active research area. There's still lots of problems where, it's not obvious what the best space filling design is. Okay, so there's still kind of a lot of open questions out in this field. So I think the best thing we can do is we can take a look at two examples. We can take a look at a design that's space filling and that's not space filling, so we can kind of get an intuitive sense of what's going on here. So here's a simple example of a design that's very obviously not space filling. So I have two factors. I have factor A, factor B. Each factor goes from -1 to +1. And the orange runs represent the runs in the experiment. Okay, so you could clearly see that there's this enormous, region here where there's no runs, okay? And then you could see that, here where I just circled, there's two runs that are right next to each other. Here in this blue region, there's a cluster of points here. So if I wanted to make the space filling, probably what you'd want to do is maybe you'd want to take this run, this run that I just circled here and maybe move it into this region, and maybe take this run and move it into this region, and so on, to better fill the space, to better cover the space. Okay, so this is a design that's not space filling. Here is a design, an example of basically the same setup where I have two factors of a design that is space filling. You can see that in this case, all the design points are kind of spread, apart very, very nicely. There's no enormous gaps. The points are roughly equidistant from one another. Yeah, no gaps, no clusters of points. So overall, just from an intuitive point of view, this design looks to be much more space filling than the previous design. Okay, and then this one here. So now let's go through kind of a bunch of different questions here, a bunch of different subtopics. So, oftentimes with space filling designs, you'll see, kind of computer simulation experiments attached to it. And I know some people that are using Statist 360 now are doing simulation experiments. So we're going to talk about, kind of what is a computer and a simulation experiment, for those of you that may not be, familiar with it. What are the, kind of the big players in the space filling design category? What are the major different types of actual designs you can use? Can you use space filling designs in physical experiments? Any strategies and tips? And finally, how can we use Statist 360 to set up and analyze a space filling design? So I'm going to talk a little bit about computer experiments and simulation experiments, because this is something that's so closely associated with, space filling designs, and we'll see why. So a computer experiment can differ from a physical experiment in the following ways. So with a computer experiment, really the only difference between a computer experiment and a physical experiment is how you get the data. In both of the experiments, you need a DOE, you need a design, and in both of these, you need to eventually have some data that you type in that you later analyze, okay? The difference is that in a computer experiment, however, it's usually a script or a simulation that's taking the factors, plugging them in to some program, and then spitting out a response, okay? In a physical experiment, you would take the factors, you'd set your time and temperature and pressure and whatever, and you'd, wait, and then you'd measure the response, and then you'd type it in. The big way in which a computer experiment often, but not always, differs is that the output is deterministic, meaning, in a physical experiment, when you repeat the same run at the same conditions over and over, you're almost always going to get some sort of discrepancy between the repeated measurements, the replicates. Okay, sometimes there's measurement error, sometimes there's different, impurities in the raw materials, sometimes, you don't quite set the temperature exactly to 400 degrees, sometimes it only hits 390, sometimes it overshoots to 410. But when you're doing a simulation and you're writing code, or you're using some sort of off the shelf simulation tool, generally, you know, when you plug in A equals 1 and B equals 7 and you run it, and you plug in A equals 1 and B equals 7 and you run it again, generally you get the same exact answer. So repeating a simulation for a given set of factors will usually, and I say usually, but you know, there are cases where there could be some you know, noise that's simulated in or baked in, will produce identical results. Okay, and oftentimes each run, each simulation can be incredibly time intensive to obtain. I mean, it could require, you know, I've seen cases where, you know, obtaining a single run took a week. So if you have an 8-run experiment or 10-run experiment, well, I mean, you can see how long, you know, it'll take you to collect that data. And now the caveat is because there is no error, meaning, you know, there's no measurement error, certain features of of traditional experimental design, things like replicates, don't make any sense. It doesn't make sense to do the same run twice if it's going to give you the exact same output, the same response each time. So that's kind of why we want to move away from the traditional, you know, central composite design with replicated center points or de-optimal design that's got some replicates in it. We want something that's a little bit more fine-tuned in this case. Okay, so the take-home message is that in a computer experiment, a computer simulation rather than a physical experiment is run to obtain the output. So here's just a little sketch of kind of, you know, a physical experiment versus a computer experiment. In a physical experiment, you know, you'd have some factors that you wanted to tweak. So here they are, tweaking the factors. You know, the R&D, you know, the aeronautical engineers here are tweaking something. Then what they would typically do is maybe do something like, you know, actually take the aircraft with some sort of configuration into a wind tunnel. And in that, they would, you know, see how the factors affect whatever it is that they're measuring, and then they write them down. Okay. In a computer experiment, instead, you'd have some sort of station or some sort of program that would actually simulate kind of what happens if, you know, the wings are set to this angle and the wings are this long and the fuselage is this diameter and whatever. So what you would do is, you know, you'd have a computer program that would actually simulate what would happen. Now, these simulations are often very complicated. They use, you know, subject matter knowledge. They use lots of physics, differential equations. So, and you don't always have the ability. You don't always have the know-how or the information needed to get an accurate simulation. So that's kind of one of the assumptions here, is that you can actually do this. And there is commercial software that will do, you know, that's kind of industry specific, that'll do simulations for specific, for like I said, for specific applications. But then what you would do is after, you know, the simulation runs, you write down the data and you go through and you analyze the data and you kind of try to figure out what's going on. Obviously, if you're doing a computer experiment, you could, in theory, you know, run it 1,000,000 times and get almost the perfect representation of the surface. But usually time is the constraint here. So, as I said, because the output has no error, replicates usually don't make sense here. And designs for computer experiments, therefore, are typically space filling. That is, they aim to cover the design space without leaving large gaps between design points. So this is what we call a maximin space filling design for 2 factors. If I were to try to build the same design as an optimal design for a quadratic model, this is the de-optimal design here. You see that it's actually optimal to replicate the corners and replicate one of the center points here. Okay. And you can see that I have far fewer unique points. This design is not space filling because I have these enormous gaps here between the middle and between the corners. So for a physical experiment, when you're interested in fitting a quadratic model, a de-optimal design could work. I mean, it's probably a pretty good choice. However, you know, we don't want replicates. Since we don't have any error, probably the best thing is that we want to try to get as many unique runs as possible. Okay, so that's really where a space filling design would come in handy. Now, I guess I'm not going to demo this, because I'm going to show this a little bit later, but in Statist 360, there is now in this design tree a option for space filling designs. There's Latin Hypercube and there's optimal distance, and I'll talk about what each of those are here in just a second. Okay, so Statist 360 has two major offerings for space filling designs. We've got the Latin Hypercube designs and we've got optimal space filling designs. And in the optimal space filling designs, we've got some that are model based, meaning the design is space filling, but you still want to fit, you know, maybe a quadratic model at the end of the day. And the other ones are purely distance based. So it's ignoring the model. It's just strictly separating the points based on distance. Okay. So I'm going to talk about both of these here in just a second. Okay. Now I do have some questions here, so I'm just going to pause just for a second just to answer a few questions. So I've got one here from Steve. Will space filling designs be available in the upcoming version of Design Expert or only on Statist 360? This is most likely Statist 360 only here. Paula asks, will we be able to view this webinar? Yeah, I probably should have mentioned that. Yes, this will be posted on our website, on our YouTube channel. The slides will be available. So if you want to rewatch something or you're not able to stick around the whole time, then yes, you can feel free to check it out later. And then finally, got a question here from Mike. Does leverage play into choosing space filling design points from a distance only point of view? If you're just looking to strictly spread out the points, it's not really looking at the leverage in that case. It's really just, you know, just to try to get the points. Now there are more complicated designs that, you know, that do things like they'll try to spread out the points, but subject to this condition and this condition and this condition. So it's like, you know, spreading it, you know, it looks to spread out the points as much as it can, but, you know, with the caveat that only 50% of the points are on the edge of the space and, you know, maybe the other 50 are somewhere near the center. So, I mean, as I said, there's a ton of kind of extensions and research being done on this, and unfortunately, there's only so much that we can do here. But that's kind of what we're looking at. So this is a one-slide introduction to a Latin Hypercube design. This is kind of one of the bread and butter space filling designs. This is mostly so that you're aware of what it is and what it can do. Latin Hypercube design. You start with K factors. When I do demos and when I do these presentations, I like to do 2 factors just because it's so much easier to illustrate this using a graph. Now, of course, when I'm doing this in the real world, you know, lots of times you'll have 10 factors, 8 factors, 7 factors, and whatnot. But you start with K factors and you divide each one into P levels. So maybe you have one factor. You have 2 factors and each one gets divided into 7 levels, and you want to test, you know, maybe 7 levels of each of the factors. The kind of what makes a Latin Hypercube design is that each factor takes each level exactly 1 time in the design. Okay, so what does that mean? Well, if you look at this, you'll see that factor B, there's basically nowhere here where I have a situation that looks like this, where I have a design point at the same level of factor B. So if I follow these red arrows and I collapse this design down to just B, I have all unique design points. B is not going to be replicated. And if I take the same design and I collapse it down to factor A, I also see that factor A takes each level exactly 1 time. So what really makes a Latin Hypercube nice is that if I do end up later maybe ignoring one of the factors, or I want to kind of collapse the design down into something smaller, it's space filling in each of the dimensions. I don't end up getting any replicates anywhere. So even if I had a 10 factor design and later I only realized, hey, you know what, I want to keep factors A and B, it's still a space filling design. If I look at only A and B, I don't have any replicates. So essentially it's kind of almost an extremely efficient way to use your time, because you don't end up with any replicates, even if you just look at 1 factor at a time. So that's really the special property of Latin Hypercube designs. And as I said before, this is a very active research area. It is somewhat of a limited design because you have to kind of make it a square and divide everything by the same number of times. But I mean, in my experience, this often gets us quite far. Okay, and the other design, space filling design that we have in Statist 360 is our optimal design. So if you've ever built a d-optimal or i-optimal design, space filling designs are generally built the same way. The current criteria really that we only offer is maximin, which this means it tries to build the design that maximizes the minimum distance between runs. That generally gets you a pretty nice design. There's also minimax designs that we're looking at, which try to minimize the maximum distance, but those are generally much harder computationally. And if you open up Statist 360, you'll see that the UI for space filling designs has been tweaked. See here we have space filling points. If you want to put in replicates, you're more than welcome to. For example, if you are doing a physical experiment, maybe you do want some replicate points. And finally, if you want to force the center point in, you can still do that here. Blocks are still a thing. And finally, you can choose whether you want to use coordinate or point exchange. Okay, point exchange is still very useful if you have a custom candidate set that you want to use. Okay, now I'm going to talk a little bit about space filling designs for physical experiments. So I know I talked, about the last 10-15 minutes about computer experiments, but space filling designs can also be used in physical experiments. In a situation when the experimental the pure error is either known or it's very, very low, meaning you have a very low error system, replicates may not be of much value anyways, because you do the experiment and you do 3 replicates at the center and you get very, very little noise. And in which case then a space filling design could be useful. The point of replicates is so that we get more power or we get more precision, and so that we also get an estimate of the pure error. In other words, if we're just doing the same run over and over again, how much error is there in the system? That's used in the lack of fit test and so on. But if we know ahead of time that the pure error is incredibly low, for example, relative to the lack of fit error, then maybe, the replicates don't really serve as much as a purpose. You might be able to get more juice out of the berry by testing more unique points. If you are performing an exploratory study on a new design space, meaning maybe you're just doing a quick experiment in a new region, a space filling design is generally going to test more unique points. It's generally going to spread the points out. It's going to cover the space as well as it can. In many cases, when people are doing these exploratory studies, what the goal is to just determine what areas of the design space are feasible or not feasible. And lots of times what people do is they'll say, okay, you know what, in here we're just getting garbage results. We don't want to experiment there going forward. So a space filling design could actually do very well in a situation like this, where you just want to see where's the cutoff for my design space. Another one, and this is just 3 of them that I've personally run into. I mean, there's probably a lot more, but these are just the ones that I ran into, doing consulting or working on actual data, is if you expect the response that you're measuring to be very curvy or spiky in a small region of the space. What does this mean? This means, let's say this is your design space and you've got a response that looks like this, where it's where it's kind of flat and curvy here, and then suddenly it spikes up in a very small region here. Okay, the more unique design points you put, the more unique design points that you have, generally that's going to increase the odds of you possibly catching this type of behavior. Now, it's not going to guarantee it, but if I have 10 unique runs here, that's certainly going to have a higher chance of catching this, this behavior, versus if I only have 3 unique runs, like in a central composite design, which just looks at low, middle, and high. So in a situation like this, where you have kind of a crazy surface here, and you know this ahead of time, a space filling design might do a little bit better at characterizing that surface when you're going to do the modeling. So this is just, a little illustration of exploratory experimentation. So space filling designs do a good job at detecting operating limits. So if you're in a new region here, you've got your two factors, and you don't really know much about how the two factors are affecting the response. Sometimes people will do a kind of a pretty coarse preliminary study just to determine kind of the operating limits and where the feasible region is. So the blue points represent, hey, we're getting useful data here. The red points represent garbage. You could, in your second pass through, you could realize that, hey, I need to add this red constraint to my design space because anything in this region here, it's just a waste of time. It's a waste of money. It's not giving me any useful information. Okay. And if you did something like a central composite design or even a d-optimal design for a quadratic or cubic model, chances are you'd probably get more concentrated points, more points along the edges. But a space filling design kind of ignores the model and just tries to spread the points out as nicely as it can. And finally, the other case was if you have a response, like if you expect your response to be very spiky or has a small region of unusual behavior. And this is, not entirely uncommon, where you've got kind of a narrow window where that's really where the magic happens. A space filling design is probably going to be more likely to detect this area of the curve. So if for example, I just had a design that had a point here, point here, point here, and point here, I'm probably not going to be, detecting what's going on over here. But if I had a design that had, 7 unique levels here, okay, chances are that these 3 runs here might have a chance of detecting, some sort of behavior. Now, of course, it's not guaranteed, but it does increase your chances of detecting that. Okay, so before I go into Gaussian process models, I'm going to just see if there are any questions here. Let me see here. So I believe that we don't have any additional questions, so we can just go ahead and keep on going here. Okay. Okay. So next question is, let's say we do have a computer experiment, we have a space filling design, and what we want to do is we want to figure out, how do we analyze this data? We want to get some sort of model, we want to get some sort of surface that we can use in optimization. How can we do this? Well, if a space filling design is used for a physical experiment or even for a computer experiment, you could always try using something like OLS regression. I mean, if you really wanted to. If you did a space filling design and you have data that's coming from a physical experiment with noise, then you could probably use something like a quadratic or a cubic model without any major issues. Now, ordinary polynomial models are often not good for modeling data that comes from a computer experiment with 0 error. Because there's 0 error, I mean, whatever model I fit should go through those points exactly because there's no uncertainty there. Okay, so let's just take a look at, very simple example here. Let's say we did a 1-factor computer experiment and we collect data that looks like this. Okay, interesting enough, I guess. If you fit if you go through Design Expert, you use the auto select and you fit a polynomial ordinary least squares model, it's going to look something like this. Okay. Like I said, the big issue here is that I know that at a equals whatever this is, about 0.2, this response should, when I actually use the model to predict and I plug in a equals 0.2, because there was no error and I'm going to get this response every single time, I should be getting a prediction exactly at that point. Same thing with here. At the design points, this curve should go through the design points somehow. Okay. So this is really what the the big difference is here. In a computer experiment and a physical experiment is we want the modeling to somehow take into account the fact that there's no error. And the way, so here's kind of the summary here. The big issue is that the model should predict the response perfectly at the design, I should say at the design points, if there is no error, and there usually isn't in a simulation experiment. It's impossible to do this with a polynomial model unless the model has as many terms as there are runs in the data set. So in other words, if you have 10 runs, you fit a 10th order polynomial, which is a pretty large and crazy model. One tool that helps with this is a Gaussian process model. It's one tool that can be used to model zero error data obtained from a computer experiment. And now there's a lot of technical details that go into Gaussian process models, which we don't have time to go into here. But I think it's best to just illustrate Gaussian process models by using a demo. Now, kind of the intuitive explanation is that, let's say I did have a space filling design that looks like this. Let's say this is my data. Is a Gaussian process model would basically start by predicting at the design points perfectly, and then what it would do is it would look a certain distance around each point, and then try to kind of interpolate based on a window here. So this is really, it's almost, if you've done something, if you've done like a non-parametric kernel density smoother, it's the kind of the essence is the same, although it's the math and the mechanics behind it are kind of different. So it's essentially almost like a weighted average type of smoother that you're using in the data. And I'm going to show this here in the demos. So let me just make sure there are no questions since we're right on time here. So with that, let's get into the demos here. So there's just two demos. Okay, and then we can wrap up. So the first demo, it's a one-factor experiment. Now the point of this, now this is not a super complicated experiment, but since I know that many people here that are watching are fairly new to this topic, the purpose of this is just to show, okay, first of all, how to set up a space filling design in Statist 360, and to show how Gaussian process models work. So this is actually taken from a textbook here. The factor is time, and it went from 0 to 100 minutes. They obtained the response via simulation. Now, of course, in this case, when they did the same simulation at the same time, it gave them the same exact response. So replicates weren't necessary here. And the simulated response was the expected output of some sort of factory process that they're running. So they have, all this information about how fast each machine can work and how much time each machine needs to wait for another one, and simulating, based on how many workers are available and the configuration of the plan. So they spent, quite a bit of time writing a simulation that, kind of tries to emulate what's going on in the factory based on, them setting some sort of production time. Now notice, these types of simulations are very common when, people are trying to design something. So something like, an intersection, if a city is trying to design an intersection, I mean, it's not very feasible to do a physical experiment where, they try to change the amount of time that a stoplight is yellow and then see, how many crashes they get a day. I mean, that's generally not a very ethical or feasible thing to do. So, I mean, things like with weather, things with, the next example I'm going to show is a mechanical joint that a medical device company is using where, you can't really tweak the joint and then put it in somebody and then have them walk around for a month and then see how it feels. So really you need, the computer to do the heavy lifting. And in this example, there was enough time for 6 simulations. So I'm going to switch over to Statist 360 here, and we're going to go ahead and open it up. And let me just make sure everybody can see Statist 360 here using the audience view. And I think we're okay here. Okay. So what I'm going to do is I'm going to do a new design. And now notice how this looks kind of like Design Expert, but you have this space filling option here now. So if you want to do a Latin Hypercube design, that's kind of the first option here, where you had, you enter the amount of numeric factors and you enter the levels of each factor here. Okay. You could also do optimal distance design. Now in this case, since it's one factor, it doesn't really matter because the optimal design, the space filling design for one factor is just going to put the points equidistant from one another. Okay, but I had one numeric factor, which was time, and it was in minutes, and it went from 0 to 100 minutes here. Now, I'll just make a note here. You could still put in constraints. So if you had, a design space that looks like a trapezoid or whatever, you would put those constraints in here, and it would build the space filling design in whatever space you define. I do want to point out here that we do have two options for the build type. We have distance only and we have model based. Distance only looks at the distance. I mean, it's pretty self-explanatory. Model based ensures that some sort of polynomial model that you specify can still be fit in a space filling design. So sometimes a space filling design might stack some points too close to one another, in which case it might not be possible to fit a cubic model. So if you are interested ahead of time in fitting a model, a polynomial model, then you'd want to select model based to ensure that the points are spread out correctly. Okay. And I got another question. Is the use of Gaussian process models predicated on using space filling design? Nope. In Statist 360, if you had a d-optimal design or you had a response surface design of some sort, Gaussian process models are still an option. They typically are used when you have when you have no error in the data. And typically when you have that, you would use a space filling design. So they're kind of linked towards one another very closely, but it's not exclusive. It's not like, oh, you do a central composite design, you'll still have the option to do a space. And I'll show how to do that here in just a minute, okay? So afterwards, you'd want to go ahead and you go here. Here, this kind of looks like our optimal interface, but now it's just reworked to put in space filling points. If you want to put in replicates, we still allow you to do that. It'll try to spread out the replicates as far as possible from one another. And some people like to force in a center point because a lot of times that's kind of their control point. So if you do put in a center point, it's going to put in the center point and then make the remaining space filling points as space filling as possible around that center point. But here, I believe we had 6 runs. So, and if it takes, a day to obtain each run, then that means that, this 6-run experiment takes a week. And then I believe the response was the output of this production process that they were working on. So again, this space filling design, this is a very trivial design, but the point is here is to show you how to set it up and how to use Gaussian process models. So here's the actual the data that they collected, and by collected I mean they ran the simulation. So they plugged in a time of 60 minutes into their simulation. And then what they did is, they saw, well, what's the expected throughput at, the expected output at a time of, 60 minutes. So what you can do in Design Expert 13 and beyond, and in Statist 360, is you can do multiple analyses now. So if you go to analysis and you click this plus button, you could actually analyze, a bunch of different models and look at them, kind of compare them. So that's actually what I'm going to do here, because I want to see how the Gaussian process model does, compare it to what let's say if you did use ordinary least squares. So now, but the first thing I'm going to be doing is I'm going to be, I just want to see what the data looks like. So I'm going to look at graph columns. You could see that at a time of 0, I get 6.1. And then you could see it kind of oscillates and levels off as I get to 100. So if I use OLS to fit this, I get a linear model as being suggested. Chances are I could, probably use a higher order model, but I get a model that looks like this. So, actually, oddly enough, I mean, this model doesn't do terrible at the endpoint because essentially a straight line is going to kind of try to connect the endpoints to one another. Okay, but you can see that there's huge deviations here at the intermediate points here. You can see that, at a time of 20, I mean, this point is almost outside of the confidence interval. The big thing here is that, OLS assumes is that there's pure error and that there's model error, okay? The model error means, there might not, the model might not predict perfectly at the points. Now, on the other hand, let's fit this using a Gaussian process model. So here, when you do a new analysis, you can choose linear regression, which is what I did in the first analysis. In the configure tab, I chose linear regression. In the second one, I chose a Gaussian process model. Okay, these special models will be enabled if Statist 360 detects that, if you have 0-1 data, it'll enable by a logistic regression. If you have data that's amenable to Gaussian process models, it'll populate this for you. Now, I only have one factor. Now, as I mentioned before, Gaussian process models, they have a window that they look at in order to fit. It tries to look at kind of its nearest neighbors and see, okay, how far do I want to look? How closely do I want to weight the neighboring runs? So Design Expert, or Statist 360, what it does is it allows you to choose that, that what we call a smoothing parameter. It's essentially a window around each point. And it allows you to choose it by maximum likelihood, by cross-validation. You can calculate this as 0.275, and then you can see what what it looks like here. You can see that this is what the Gaussian process model looks like when I use one of the suggested smoothing parameters. Now notice how this makes a lot more sense, because at the design point, the model goes through the design point, and the confidence intervals also have a width of 0 at the design points, because I know that with 100% certainty, that's the response there. And you can see how they kind of get wider as you get, between 2 points, but then they converge back to 0. And you can see that they're wider at the endpoints and so on. So this is because there's no error here. So this is really kind of the more appropriate tool. Now somebody say, well, what if I do have error? Well, in that case, you don't want to use an OLS model, or you don't want to wait until we put in some of the Gaussian process models that do allow error, because there are extensions that model error as well, but in a computer experiment, we often don't have error. So this was kind of the more pressing case for us. Now, I'm going to stop this example here and just say, you could, when you do optimization, when you do point prediction, when you do all of these things, it's going to function just as if though you had fit an OLS model. So if I want to maximize the predicted response, the numerical optimization is going to tell me that I need to be here somewhere. So I can go to the numerical optimization, go to output, and I want to analyze the Gaussian process model. And I want to maximize this, and maybe I'll stretch this out a little bit to 12. And in my solutions, I can see that the maximum is right here. So once you fit the model, everything else works exactly the same. Okay, so, and it's really, really interesting to see, the confidence intervals here. They're very different. If you use the OLS confidence intervals, you're going to be getting, what looks like there's way more error in the data, because again, OLS assumes that there's measurement error, that there's pure error, and that these design points here are not exact. Okay. Now, for the sake of time, I'm going to move on to the second example. So again, really the key here is that there's, here, the model screen here allows you to put in, whatever you want to put in. Sorry, let's go to the Gaussian process model. Well, I only have one factor, time, so that's the only one I can put in. It does require a smoothing parameter, but there's two good ways that Design Expert can do it. One is cross-validation, which is basically a predictive measure, and another one is maximum likelihood. And then there's also, you're also more than welcome to try manual input, which, means you can type in, I can type in a larger one here if I want to see what's going on. And I end up getting a model graph that looks like this. This basically, the model still goes through all the points, but now notice how the confidence intervals are, how tight they are, because a smoothing parameter of that large tells me that basically, it's looking at the entire window, so there's less uncertainty. The smaller the smoothing parameter, the smaller the window it looks in. So I do apologize for going a little bit over time here, but I'm going to go into this second example very quickly here. So the second example is it's an actual example from the medical device industry. And unfortunately, I wanted to try to make, use the actual data they had here, but there was some stuff that had to be obfuscated for confidentiality. But the R&D team was developing a new artificial joint, and they wanted to see how the stiffness of the joint changed as two factors were varied. One was the, I think, I don't even remember. One was, I think, maybe the thickness of one of the composite materials, and I can't remember off the top of my head what the two factors are. But it's very difficult to perform this as a physical experiment, as you might imagine. I mean, you have to actually design it, build it, and then insert it into somebody, and then, have them walk around or whatever for some amount of time to see what's going on. So as a first step, the team did this as a computer experiment. So they were able to create a simulation that described how the stiffness of the new joint changed as two factors were tweaked. So basically, they took lots of equations from physics and lots of subject matter knowledge and kind of, wrote a simulation to take these two factors they're tweaking and see kind of how the system plays out. If I recall correctly, the simulation was very time consuming. One run took 40 hours to obtain. Now, I don't know if that's because, it could just be that the simulation was poorly written. It was written in a language that was maybe very, very slow. Maybe it was written poorly or done on old hardware. So who knows if, 40 hours was really, but that's what was reported to me. And there was enough time for 8 runs, okay? And I believe what they did is they did this. So I'm just gonna go ahead and show this. I'm not gonna go through the entire the build process, but I believe that this was done as this is joint. I believe that this was done as a Latin Hypercube design. I can verify that by looking at the DOE and the graph columns, or I could just take a look at the summary here. Yeah, this was a Latin Hypercube. So this was set up as a Latin Hypercube. You can see the 8 runs are here. Let me color by none. So you could see here that this is space filling, but kind of the unique feature here is that A and B were never replicated. Okay. So if I go to stiffness and I could use linear regression, or I can use my Gaussian process model, start analysis. Now I have 2 factors that I could put in, and by default, it chooses maximum likelihood, which is fine. I mean, you could also use cross-validation to get that smoothing parameter, 4.106 in this case. And if I look at the model graph here, the 3D surface, this is what model I'm getting here, okay? This is generally, this looks kind of like almost a two-factor interaction model. If I went back and I calculated this using maximum likelihood, I get a model graph that looks something like this. So similar, but a little more waviness in the curve here. Okay. Same thing, if I wanted to optimize, if I want to include this as part of an optimization or any of that stuff, everything else proceeds as normal from there. So really the big key take-home message is that the surface goes through all of the points perfectly. Okay. And yeah, but there's obviously uncertainty in between when you're interpolating. So why don't we wrap things up here, since we're already at 50 something minutes. Space filling designs, to me, they're a very interesting class of DOEs that have many practical applications. And as I said, a lot of times they're primarily associated with computer experiments, but they can also be used in physical experiments as well. I mean, sometimes I've talked to people who said they just like space filling designs because they look prettier, they cover all the gaps, and they make people feel more safe that there's no large region that goes without points. So, I mean, it's perfectly fine to use a space filling design in traditional experimentation. Now, Statist 360, it offers a solid foundation for experimenters wishing to use space filling designs in their own work. Now, this doesn't apply to a lot of our design expert users. A lot of them don't, they're never going to do a computer simulation. They're always going to do their central composite design or factorial design. So this is fairly advanced stuff. And more features will be released soon. Space filling designs for mixture experiments, designs that incorporate categorical and numeric factors. I mean, additional Gaussian process models, tools, and statistics and diagnostics. So this is really just a first step to see, what we have. Now, here is, let's see here. Here is just a little aside before I conclude. Statist 360 does have the ability to write Python scripts. Now, a lot of times people will do simulation in languages like Python. That's why I want to mention it here. So With Statist 360, what you can do is you can write scripts to automate routine processes. You can create simulations. You can combine features of Statist 360 with features from relevant Python packages. There's one Python package called scikit-learn, which has a lot of tools in there that are possibly useful to computer experiments. So you can, do something in Design Expert, then take it out, then use scikit-learn, then send it back to Design Expert. Then you can write a script that basically automates everything for you. I mean, one thing that we get is we get a ton of requests for, hey, I want this plot that does A, B, C, D, E, F, and all these things that that somebody needs one time and they're never going to need it again. If you know how to do any scripting in Python, you can use something like matplotlib to customize plots exactly how you want them. And as I said, it allows facilitates import, basically data I/O, import export between Design Expert and other software. So in Statist 360, you'll see that there's a script editor button here, and it'll allow you to write your own custom scripts. So with that, I want to thank everybody for listening. Like I said, if you have any questions, you can feel free to email me here. Okay, I'm martin@statist.com. There's a demo of Statist 360, a free trial available on our website. So if you do want to check it out, take it for a test drive, that's fine. We do also have a special offer right now. If you're on a subscription, meaning a network or a single user subscription of Design Expert, you can actually upgrade to Statist 360 for free for the remainder of whatever amount of time is left on your annual subscription. And then when it comes time to renew, you're more than welcome to choose, between, hey, I want to keep using Statist 360 or Design Expert is enough. So it's a totally no hassle, no obligation trial. We just want people to start using it and giving us feedback so we can go there with it. So if you have any questions, feel free to reach out to me. If you have any questions on purchasing or that, you can go to you can email sales@statist.com, and they'll be able to give you more information on that. So I want to thank everybody for joining. I know it was kind of a long, hour-long presentation that could be possibly early in the morning. So I want to, again, wish you a good night, a good afternoon, or a good morning, depending on where you are. And again, if you have any questions, feel free to reach out to us at any time. So thank you again, and good luck in all of your DOE going forward. Bye-bye now.